Hello everyone, today I'm going to give you two more weapons to deal with more complicated circuit questions. And these two weapons were developed by and organized by a German scientist by the name of, I'm going to have a lot of difficulty pronouncing his name because that is in German, is Gustav Kirchhoff. Gustav Kirchhoff. So Kirchhoff's law, that's what we come to know about these two rules. One of them deals with currents and the other one deals with voltage. And they actually are very intuitive rules that makes perfect sense once we explain it. Okay, so the first one, Kirchhoff's current law. Now, before we discuss this law, let's remind ourselves what is current. Current is the amount of electron charge, in this case, carrying energy for us in a circuit is electron. So the amount of electron in coulombs passing by a certain point in a circuit per second. And now we remember from Mr. Chang's Pizza Hut model, what are those electrons? Those electrons are delivery boys or girls. They are delivery guys or delivery ladies, right? So they are delivering the energy for us. The energies are the voltage, right? In this case, the pizza. So first law says this. Now the first law, it says the sum of current going into a junction. Now what is a junction again? This thing. This is a junction. A junction is basically a point with more than one path that you can split up. So the sum of current going into a junction is equal, okay, so it's equal to the sum of currents leaving the junction. Okay, so the sum of current going into a junction is equal to the sum of current leaving the junction. Now, that is basically just a conservation of charges. When you think about it, that means the amount of people going into a corner should be equal to the amount of people going out of a corner. Now, think of it in, a couple different ways. For example, instead of talking about current, now, so let's say we have some current going into this way. Let's call this I1. And some current, so it's going in, and then you have some current going out, which is over here, I2, and you have some current going out from here too, I3. Okay, so now who is going, which current is going into the junction? The one that's going in is this one. This is the current going into the junction. It's going in to this corner right here. Now, these two are the one, this one, and this one in here, these are the current that's going out of the junction, right? So these two are the currents going out of the junction. Now think about it. Remember, current in our model can be looked at as electrons running in a circuit. So the amount of electrons running in a circuit. So for example, if I'm Pizza Hut, right, I have my pizza joint, and so let's say I have 5 amps of current going into the junction, 5 people going into this little corner. Then how many people should exit that corner? 5, right? I mean, together, that should be 5. So for example, let's say I2 has 2 people coming out, then I3 would have 3 people coming out. Because, think about it, right? I send in 5 people, and they arrive at this little junction point, and they decide to split up so that they can deliver the pizza to different people. So how could the number of pizza delivery personnel going in different from the number of pizza delivery personnel coming out, right? That doesn't make sense if the number is any different. I mean, what happened at the corner if they disappear? So they teleport? Or maybe they were eaten by something? No, right? I mean, so the amount of electron going into a junction should always equal to the amount of electron coming out of a junction. You can change the word electron to anything. The amount of car going into a junction should equal to the amount of car exiting that junction, right? That makes sense. If it is not equal, then it will be very, very confusing. Right? Now, so this law right here is basically saying that, so for example, in this case, we can conclude that I1 must equal to I2 plus I3, just because anything that's going into a junction in terms of numbers of electrons or amount of electrons should equal the amount of electron coming out of it, right? So the junctions So we can write down the equation. So for any junctions, okay, the sum, remember this sigma notation means sum of current going into a junction is always equal to the sum of the current going out of it. Okay? So essentially what we are saying is that charge, in this case, the amount of electron is always conserved. Okay, so charge is conserved. You can have different amount of charge leaving a place compared to the amount of charge coming in. That just doesn't make any sense. So this law, Kirchhoff's current law, is also known as the junctions rule because it deals with junction. So it's called junction rule. Okay, so the amount of current entering a junction equals to the amount of current exiting that junction. Okay, now moving on. So I just have to put that remark in here. So in Mr. Chang's Pizza Hut model, right? Basically, the junctions rule translate to enjoy your meal, but don't eat the person who delivered the food for you. Okay, so enjoy your Uber Eat dinner or DoorDash or other company that you might order takeout from, but don't harm the person who's giving you the food. Okay, let them come, let them drop their food, give them tips, then say thank you and let them go. Okay, so the amount of people going into a junction is equal to the amount of people coming out of a junction. Okay, so that's basically the rule that we have in that case. Now, so then we have a voltage rule. Okay, so it's called the Kirchhoff's voltage law. So we have a junctions law and we also have a voltage law. Okay, so one is for current, the other one is for junction. Okay, so the voltage law states this. For any closed loop, that means a loop is a way that you can draw a line without leaving your pen on a circuit. For example, this blue line that I'm drawing right now is one loop. But that's not the only loop I can do in here. I can also draw a loop this way, right? That's also a loop. A loop in our Pizza Hut model is a delivery route. Okay, so it's a delivery route. Now, so for example, in this picture, we can draw two loops. So what happened to any of the loops? Okay, so for any closed loop, the sum of voltage gain is equal to, is equal to the sum of voltage drop. The sum of voltage gain is equal to the sum of voltage drops. Okay, so what does that mean? Now, voltage in our model is pizza, is the energy carried by those food carrier, by those electrons, right? So what happened when you go through the battery? Okay, so when you go through the battery, you pick up voltage, right? You pick up voltage. So when you go through a battery, you always pick up some kind of energy. Okay, now in this case, the current goes in this direction. So for example, so let's say like the current goes in this direction. So an electron will enter the battery, picks up 5 volts. Now, this electron, let's color in blue, is going to carry 5 volts, 5 pizza. And this electron is going to go around and deliver food according to this blue route. So it goes around like this. So it goes in here, and then it goes down here, going through R3, okay? And then it goes to the left, and it goes up, it goes to R1, and then it will go back to the battery. So what happened is, now what is the equation or the rule saying is that the amount of pizza energy, voltage that you pick up from battery should equal to the amount of pizza that you delivered in your route. Now that makes perfect sense. So for example, if the electron pick up 5 volts from the battery, then let's say you know that the electron drops maybe let's say 1 volt in here. So one of the pizza is being consumed in here. So we can say the change in, okay, you know what? We can say negative. Let's say the change in voltage is negative 1 volt. Then what is the change in voltage at this location? Now, if you look at the delivery route for that electron, it picks up energy at the battery, and it has to drop its food at customer number 3 and customer number 1. Now you might say, well, what about customer number 2? Well, customer number 2 is not on his or her delivery route. That is for the orange electron to do. Okay, so there are billions and billions of electrons coming out from the battery at a time. They don't all have to go in the same direction. Remember, they split up at junction point. So the blue electrons doesn't have to care about R2 because it's not part of its route. Now we just randomly label them. So we know for sure that electron blue electron is going to drop. So let's say, for example, 1 volt at R3. Then how much does it have to drop at R1? Well, it picks up +5 though. So therefore it has 5 pizza. If they deliver 1 pizza here, then it has to deliver 4 pizzas over here. Because in total, the total amount of pizza that he deliver should be the same as the amount of pizza that it picks up. So you have a +5 volt, and you should have a -5 volt in your delivery route. Okay, so if you have to stop at 2 locations and you know how much voltage you're dropping in one of the locations, then it's automatically assumed that you will also be able to find out quite easily the amount of voltage that you're dropping at the second location. Now the orange electron is going to go through exactly the same thing. So this orange electron, which is going to take the other route, is also picking up 5 volt from the battery, because that's actually the side from the battery. I mean, any electron going through that 5 volt battery picks up 5 pizza. So this electron though, however, goes this way. So it goes in here, and then it entered, so it exit the battery, enter this junction point, decide to go left instead of going right, go through R2, and then it will meet the blue electron again, and they will all go down here, go to the right, and then go up. Now, notice that it drops 4 volts. This electron also have to drop 4 volts at R1. Everyone has to drop 4 pizza when they go through this house. Doesn't matter if you're blue or orange, because you both have to go through that customer. So that means, how much does it have to drop? How much will it drop at R2? Well, in this case, the voltage drop at R2 must be 1 volt, right? So V2 must be 1 volt, because it drops 1 in here, and it drops 4 at the R1, and then it comes back with nothing and go back to Pizza Hut and picks up more pizza and do the whole thing again. So this is actually a way to explain why last time we said in parallel circuits, right? When things are collected in parallel, these two are collected in parallel, the total voltage drop on the 2 branches should be exactly the same, because the blue electron and the orange electron, they both have to go through this house R1. So they drop the same amount at R1. Now the only difference between the blue and the orange electron is the blue electron goes through R3, the orange electron goes through R2. But they have to drop 4 at R1 regardless. So they only have 1 more pizza left, and each of them only have 1 station left, so therefore they must drop the remaining pizza over there. Now, a little bit of a side note, right? For example, if you have, so let's say a junction point, one side with 2 electrons, the other side only has 1, then what happened in this case? So one side has 2, the other side only has 1. Well, then they will have to drop like this. So let's say you know that it drops like 5 volts in here. Okay, so let's say this is R1, this is R2, this is R3, and these are in parallel, right? R2 and 3 is in series, but then R1 and R2, 3 together is in parallel, right? So now, if that's the case, right? So if you know that this drop is 5 volts, then it will only make sense, okay, if the combined drop in here is also 5 volt. So if you combined it, it should also be 5 volt. Because the electron either go this way and do its delivery, or it goes this way and do its delivery. But it doesn't matter which way they go, they should end up with the same amount of pizza drop once they enter that junction point. Okay, so parallel branch like these always have the total voltage drop being exactly the same. So if we know that, so for example, let's say R2 is negative 2 volt, then R3 must be negative 3 volt, because together it has to be negative 5 volt. Okay, so parallel branch always have the same voltage drop. It doesn't matter if it's 2 branches or 3. Sometimes you might have a circuit that has like an extra branch in here. Then yeah, okay, cool. Then it will be 5 volt drop in here too, right? It's also 5 volt. Okay, so it doesn't matter how many parallel branches you have. Okay, so now let's summarize that rule. So for any loops, in a circuit, doesn't matter what which one you draw. So for any loops in a circuit, so we have, so let's use blue, the sum of voltage gain, okay, is equal to the sum of voltage drop. Okay, so for any loop in a circuit, the sum of voltage gain is equal to the sum of voltage drop. We call that the conservation of energy, or in our analogy with the Pizza Hut model, is the sum conservation of pizza. So energy or pizza is conserved. If I give you 10 pizza, so you pick it up from my shop, from the battery, right? And I ask you to deliver it, you better deliver 10 pizza before you come back. If you only deliver 9 pizza, you're not doing your job right. You ate one of my pizza, or you lost it, or you dropped it. So I should deduct some salary from you. Or if you deliver 11 pizza, then cool, I guess. I only gave you 10. I don't know why you have 11 to deliver. But you see, it doesn't make any sense if the number is not exactly the same. So the amount of pizza you pick up from the Pizza Hut should be equal to the amount of pizza that you delivered in total. And you and your friend, let's say you both work from the same pizza joint, might have different delivery routes, but at the end you're delivering the same amount of pizza, because I'm giving you guys the same amount of pizza to begin with, right? So this voltage law, because it has something to do with loops, is also known as Loop's rule. Okay, loop rule. So the two Kirchhoff's law, we have a junction rule for current, and we have a loop rule for voltage. Okay, so these are your new weapon. Armed with these, right? So armed with these new weapons, you will now actually have a much better or easier way of solving some of these questions that, for example, you tried last time. Okay, so now if you're solving question with Kirchhoff's law, here are some pointers. First of all, you draw a circuit diagram if one is not provided, which is the same as last time. And next to each resistor, indicate VIR, same as last time. Next to each battery, indicate V total, I total, R total, the same as last time. Indicate the direction of current. Now, so direction of current. So if you have the battery installed like this, remember, current goes this way. Okay, the current goes this way. So it goes from the, so it goes like, so this is the positive negative terminal. So there we go. Okay, so current goes, oops, wait, there you go. Current goes this way. Electron actually goes the other way. So this is the negative terminal. That's the positive terminal. There we go. That's why something was weird. Now, so then what we do is apply Junction's law or Current's law to each junction. So apply Current's law to each junction and see if you can find a junction that only has one unknown. So if you could, okay, so with only one unknown current. Okay, so for example, if you have a junction that has current going, so for example, it could be like a complicated junction like this, right? So it could be wire going crazy like that, and you have one junction point in the middle. But as long as you know, okay, so let's say this is, people tell you that this is a 5M, and then there's something in here and say this is 2M, and so the current's going that way. And then maybe there's another one entering in, which is 3M. As long as there's only one thing you don't know. So for example, in this case, there is only one current you don't know. You know the other three. Which one is in, which one's out, you have to be careful about it. But the total in equal to total out, that's the rule. At a junction point, total current in equal to total current out. Now, this is going in. This is going in. That's going out. Okay, so what is the total amount of current going in? So the total amount of current going in is 8M, right? 8 amperes, 5 and a 3, right? Now, the total amount of current going out right now, for example, is how much? 2. So what is the missing one? Okay, so we just ask a question like that. So total amount coming in is 8M. The total amount coming out should be 8M, but I only have 2M's going out right now, so I'm missing what? 6M going out. So I'm missing 6M going out. So we can predict not only the magnitude, but also the direction. Again, this is saying that 8 people go into that corner. How many people get out of it? 8, right? Not 7, not 9, 8. It has to be 8 people coming out. 8 people going in, 8 people coming out. Okay? It makes sense that way. All right, so you find a junction that only has one unknown. Now, if you could, right? So, I mean, a lot of these things, at the beginning, when you begin the question, you might not have a lot of things. But as you progress, you will have more and more information. And you might be able to find a corner that only has one unknown current. Then you can use the other current to actually figure out what is that unknown current. Okay, so now, what if you don't have a location with unknown current? Then you actually do voltage law. So you try the voltage law, which is the loops rule. So you apply the voltage law to each loop. Okay, so you might have some loops in your question. So you apply each loop. So you draw some loops, and then you find out if there's a loop that you have all the voltage drop, just one missing voltage gain, or the other way around, right? Maybe you have the voltage gain and then you have some of the voltage drop, but you're missing like one. So again, so in this case, you are trying to find unknown voltage. Okay, so you're trying to find an unknown voltage value. Now, then, okay, so what would that look like? So a lot of time, so the way I look at it is I will try to draw a loop and see, okay, so computer is lagging a little bit. I'm sorry about that. Okay, there we go. We're back. Okay, so I will try to look at a loop and see if there are any ways that I can find. Now, usually the voltage gain is given because it's from the battery. So I will look at and see if I can find the other voltage drop and see if there's one missing that I can find, and then I will make them equal to each other. So now, final note. Sometimes you might also have to calculate so sometimes the equations or the circuit is much more complicated than you know how to even start, sometimes. So what you need to do is to find the equivalent resistance from the parallel branches, okay? So that you can simplify the equation a little bit. So sometimes you might have too many parallel branches and you don't know what to do with it. So you might need to find the total resistance or the equivalent resistance from those parallel branches. Okay, so equivalent resistance. Okay, so the E is gone, didn't register. Equivalent resistance. That means you might need to combine some of these parallel branches into one so that you can actually use it to calculate the rest of the question. And at any location, when you're in doubt, if you have 2 out of 3 things from current, voltage, or resistance, you can always find the missing third one. So Ohm's law all the time to help you. Now, and if the question asks you for power, usually you cannot get power immediately. You can only get power after you're almost done with everything else. You have the voltage and current at that location, or you have the current and resistance at that location, or you have the voltage and resistance at that location. You can only find current if you have 2 out of the 3 things from the Ohm's law also. You can only find power. You can only find power if you have 2 out of the 3 things from Ohm's law. Okay, so if the question is asking you for power, you have to solve for voltage and current at the location first before you can actually find the power. Okay, so we're going to look at 3 examples very quickly. The first example is actually going back to your last day's notes. So let's go back to the last day's note. Now we leave one section blank, which is this right here. This is from last day's notes. It's for note 2. Now we did this question already. See, question 5, right? But look at how long it took us to actually do this question if we only know the rules that we learned from last day. And we're going to redo this question, okay? And we're going to do it very, very quickly this time. Hopefully, we can do it quickly this time, right? Okay, so let's see how this is done. So we're going to redo that question that we did last time at the end. But now we have Kirchhoff's law. We have the voltage law and the current law to help us. Okay, so now, all right. So the way I would do this, the beginning part is actually very similar to what we did last time, which is I will have to find the total resistance first. So before doing that, I will then, okay, so I'll first find the equivalent resistance from this parallel branch in here. So I'm going to label them. So this is R1, and this is R2, and this is R3. So I'm going to have voltage and current next to it also. So I'm going to find R total. Now this is V total in here. So I'm going to have to find, I wanted to find the R total, but R total is not R1 plus R2 plus R3. R2 and 3 is in parallel. So again, to find it, I'll need to do, so step 1. So to find it, I'll need to do 1 over R, I guess I'll call it R23, because I'm combining 2 and 3 in parallel. It's equal to 1 over R2, which is 6 ohm, plus 1 over R3, which is 18 ohm. So I'm not going to write down, I'm trying to save time in here, so I'm not going to write down R2 and R3. Just write down the number. There we go, right? And then we will have to calculate what that final number is. So which is R23 is equal to, so in your calculator, I will do it in, I will just do it on my calculator. 1 second. So R23 works out to be roughly exactly 4.5 ohms. Okay. So now with that, I can find R total. Okay. So R total is when R23, so this is now combined into like one big one. Okay. So it's called R23. And this is in series with the R1. So now R total is R1 plus R23. Now, if you don't remember the logic of why this is now in series, please go back to the question just above, like up there, to see the picture that we draw. Okay, so I'm adding them together. R1 is 8 ohm, and this is 4.5. So together, R total is 12.5 ohm. So far, it's exactly the same as last day, but things are starting to change. Things are going to change. Okay, so next step, I'm going to find the voltage drop over here. I'm going to find V1. Okay, because I have R total, and this R total, right, is going to help us. So this is R total, which we know is 12.5 ohms. So R total is 12.5 ohms. So with, hey, wait a second, that's 2 out of 3 things. So what does that mean? That means we can find the third thing. The third thing is I total. Okay, so I can find the I total. Now, what will be the I total? I total is going to be Ohm's law. V equal IR. Okay, so I total is pretty easy. So the voltage drop is going to be what? So what's the voltage drop? The voltage drop is, well, voltage gain actually in this case, 20 volt, and the equivalent resistance is 12.5. So 12.5 ohm. So the I total, just divide them. So I total is 1.6 amp. Okay, so I total is 1.6 amp. Now, I'm going to use this I total to figure out V1, voltage drop number 1. Okay, so this voltage drop number 1, now, actually, this number is already I1, so we answered one of the questions already. Why is it I1? Look at this. The current split up. Now, so the current goes this way, and at this junction point, it's split up into two different, but then it joins and combine into I total again. So as it goes through the resistance number 1, I1 is the same as I total. So 10 people, look, think about it. After they go through this R1, it has to go back to Pizza Hut. So that's the last stop they have to make. They should have all the people already in groups, right? So this I total breaks into, maybe if you want to call it I3 and I2. So I total breaks at the junction point, okay, break up into I2 and I3, and then recombine after that into I total, and then go into the resistor number 1. So that I total is also I1. So we have one of the three things that they require. We want all the current. Okay, so now I'm going to do this next thing, which is figure out V1. Why do I have V1? Because I already have two out of the three things. This is now 1.6 amp. So I have the current, I have the current and the resistance. So therefore, I can figure out what is the voltage. Remember, once you have two out of three things, Ohm's law. So V, voltage, right? So we have V1 equal I1 R1. Now in this case, the voltage is going to be simply just multiplying that 1.6 by 8. Okay, 1.6 by 8. So V1 is done. So what is V1? Now, V1 turns out to be, let's see, 7.2 volts. Okay, so if you multiply 1.6 by 8. All right. Now, how does that going to help us do anything? Well, okay, now we apply Loop's rule. Loop rule from Kirchhoff's law. Okay, so I'm going to erase, or actually, you know what? I might not have to erase. I'm going to just use a different color. So I'm going to look at this loop. Okay, this is one loop. So in this loop, how many stations did I actually have to stop to deliver pizza? 2. R3, R1 is where I have to drop pizza. Well, where did I pick up any pizza? The battery, which is up there. That means, okay, if I label this V3 and this V2, now that means within this green delivery route, for example, right, V total must equal to V3 plus V1. They must be. Because the green electron, the one that goes through the green route, picks up 20 pizza at the battery. 20 pizza at the battery. It drops 7.2 here. So the remaining pizza must be dropped over here. There's only 2 stops for the green electrons to deliver. So if the voltage is not consumed in R1, it must be consumed in R3, because when you go back to the battery, it has to be empty. The electron has to have nothing, and then pick up 20 more pizza and do it again. So therefore, this gives us a very quick way of finding out what V3 is, because we have V1 already from the top, 7.2. I pick up 20 pizza, I drop 7.2 at V1, so V2 must be the rest of it, right? So V2 must be the rest of it. So therefore, V3 is then done. V3 is 12.8. Right? It's whatever is the remaining piece. So it's 12.8 volt. And if you know V3 is 12.8 volt, then suddenly you have 2 out of 3 things. R3, V3, now you can figure out I3. Also, by the same logic, because you can draw arbitrarily, the green path was something that we draw arbitrarily. You can also draw a path like a loop like this pink one, which goes through R2 and then come back to the battery. Goes through R2, R1, and then come back to the battery. So remember, parallel branch always have the same voltage drop. So V2 and V3 is the same. So I can also say this is also V2. I only need to do, if I know that this is V2, I have 2 out of 3 things on resistor 2 also, which means I can figure out current number 2 right now. Current number 2 and current number 3 is now done. 2 more Ohm's law, we are good to go. So V2 is I2 R2. V3 is I3 R3. Ohm's law, right? On both. Now, V2 and V3 are both 12.8. So 12.8. R2 and R3 is given in the question. R2 is a 6 ohm resistor and R3 is an 18 ohm resistor. Divide both sides by the resistance from the voltage divided by resistance. I have I2 done. And I2 will be 1.2 amp. And I3 will work out to be 1.6 amp. Okay, so now they're all done. So we used the loops rule this time. We didn't actually use junctions rule because we were never at a point where we only have like one unknown current out of the 3. So we have I total coming in, but we don't know how much goes into R2 and how much goes into I3. So that doesn't work. Okay, so wait a second. I think I wrote down one of the number wrong. So give me 1 second. Okay, I found a mistake. I3, I was looking at something else. I3 is actually 0.4. Okay, 0.4 amp. That is the correct answer. Okay, now, good, right? Okay, there's actually something funny in here, which is a little bit, I don't know if some of you will realize it. If you look at these two numbers, the current 2 and current 3 is off by a factor of 3. If you look at the resistance value for R2 and R3, it's also off by a factor of 3. You realize that? But it's reversed. So R3 is 3 times bigger, but I3 is 3 times smaller, right? It's 0.4 compared to 1.2. Now, it turns out that, for example, it makes sense because higher resistance means more traffic. More traffic means less people would like to go through, right? Longer waiting time means less people would like to go through. And the amount is exactly inversely, it's kind of like inversely proportional. So if the current is if the amount of resistance is 3 times more in row A compared to row B, then there will be exactly 3 times less people going into row A compared to row 3. So that's actually something that you can use to check if the numbers are nice, right? So for example, in this case, that current, the resistance 2 is 6 ohm, resistance 3 is 18 ohm. So your current should be the reverse version of it. And this will actually give you a way of double checking your answer. Okay, now I'm going to stop here and I'll post the note for the other 2 example, which is on the original note 3 page as a separate video. Okay, goodbye. See you then.